type it out there for the world to see. I thought I'd let you guys know first. They contacted me, so if any post we want, let me know, like flag this and say, cut this to the discourse. Otherwise, I think they're going to, I don't know how soon, but soon enough, right?
Will that still give us a room, a little private room and everything?
I don't know if it give us a little room, because obviously everyone can see everything on discourse, but that's a good question. I can take that back.
Just curious. I like our little channel.
I'm sure if we still want something, we can put something else together.
Yeah.
Yeah. The thing is with Slack is, I think after 10,000 messages, it goes away. So as it keeps growing, and then the only way to keep it is like $10 a user. It's like illegal for us.
And I don't think they want to pay that.
Okay.
Okay, is everybody in here? Yes, everybody's here. Okay. We have our first presenter, Anya. Are you ready or not?
Oh, I didn't know I was going to be first.
Oh, well, you can have Daniel go first if you want.
Well, so yeah, in our chat, we were, I saw Daniel's post and he was going to go over freeze and
I don't mind one way or the other.
Yeah, I think yours will be more coherent. So let's, I think it will be better.
Okay, I'll just do that. I didn't know what to call it, so.
That works.
And you are now co-host. Take it away, Daniel.
Wonderful.
Stop share.
All right, can we see my notebook?
Yeah.
Yes, okay, great. So basically, given the emphasis on the course so far and all of the things Jeremy has been saying about transfer learning, it struck me that the part of chapter 5 that focused on freezing and unfreezing the models and training one cycle at a time and things like that was pretty important, so I wanted to go through it again. In this particular case, I took the data set from chapter 6 and also the problem setting, so it's a multi-label problem on the Pascal data set, and applied the sort of step-by-step transfer learning process from chapter 5 to it. So the basic idea here is that we are starting with a pre-trained model. I use Resnet 34. As with everything with transfer learning, Resnet 34 is trained for a different task. In this case, it was trained on the ImageNet dataset, which has millions of hand-labeled images, tens of thousands of categories. In this particular situation, we're looking at the Pascal dataset, which has 20 categories. I don't have any idea what the label of overlap is with ImageNet, but it's clearly a different problem setting. Before I dive into it, I just want to throw in a note on workflow, because we always get into variations on that. I hadn't really used Colab before, but I've actually found it really seamless to first work on a notebook on my local machine, hit a point where I want a GPU, push all of my changes to a Git repo, open it up from the Git repo in Colab, run whatever I need on the GPU, save it from Colab, and then resume editing locally. Just if you're interested in yet another approach to all of this, I found that to be the easiest and freest way to work on it so far. So anyway, back into it. Preparing the data, this pretty much exactly follows the process of chapter 6. So in this case, we set up a pandas data frame that has labels and associated file paths. So set up the functions to get the paths, to get the labels, to split the data based on the is valid column, set up the data block, set up the data loaders. Again, exactly what we did in chapter 6. There's nothing new here. And then you can see we have these multi-labeled images. So the objective from chapter 6 was to try to get all of these labels correct with our model. Did anyone have any issues with the data when going through chapter 6? Anything you wanted to stop and look at a minute?
So ResNet 34 is not a multi-label model. Is that right?
I think it was, if I recall correctly, but I'm
okay.
Also not sure that it matters because I think it's more about our choice of metric.
Okay.
But
and this is,
we can
okay. Yeah, I'm just
think about
trying,
that.
I'm just trying to lay out. Okay, and then this is a multi-category problem.
Yeah, because if I recall in chapter 6, in chapter 6 we still did use Resnet. So we've used Resnet in both single and multi-label problems, just following the book so far.
Okay. Okay.
So that's applicable to both of those problem settings, and it just depends. In chapter 6, we defined that accuracy multi-metric, which took it from defining accuracy based on yes or no, this is right or wrong, to did you get all of the labels or not. So I think that that's the major change. Okay. And then it's a loss function that's also different. Does that make sense?
Yeah. How about your little function that splits the label into separate things? Where is that? Right.
The splitting into the validation set?
Well, actually, that gets the label.
Oh, the separating one.
Yep. Let me see.
That's this one. This is also just right from the book. It's this dot split method.
Okay, so it's in the labels column. It's a multi-word column that you split on space. Okay.
Yeah. So let's see. I don't think I have. I guess I did not show the data frame here, and I'm just looking at this as flat HTML, so I can't pull it right now. But I believe they were just separated by spaces. Mm-hmm. And so this says like look for words separated by spaces and split accordingly.
Okay, that will return a list, I assume, the split.
I believe so.
Okay, I'll keep that in mind as we go through this.
Yes. Yeah. Preparing the model, again, same thing as chapter 6. Haven't gotten to any of the new stuff yet, but this is where we have the accuracy multi. So I didn't do a super deep dive in testing this function out or anything, but the general idea is that instead of testing if one category correctly matches the label, it's checking if multiple categories correctly match multiple labels. So the meat of what I wanted to get into was the transfer learning. So in this case, we have a CNN. We start out right from the beginning with a CNN learner object, which I defined right up here, that again has not been trained for the current task. It hasn't been trained on Pascal. It's never, depending on if there's any overlap in the images, it's never seen the Pascal data set. So when we initialize that model, we start with just random weights on the final linear layer, the linear layer that's going to actually output predictions, basically. Mm-hmm. So again, Resnet was trained on something that had more than 20,000 categories. Our data set has these 20 different set of things that we're looking at. So yeah, we've got a different number of classes. The classes are different. The final layer that was there in the original Resnet model doesn't really help us. So what do? We throw out that layer when we initialize our new CNN and the new data, and we replace it with a new final layer with the correct number of activations, 20, for our present problem. So first, let's just see out of the box what happens with this brand new layer that we've made. So just do a learn.validate 60% accuracy. It's actually higher than I would have expected. Possible I did something wrong, but it's random weights, not gonna do much for us. So to make this model actually usable, we need to train the weights. And over the course of this, well, so we do this in sort of two separate steps. First of all, we want to train the weights on this final linear layer. All of the other weights have been trained in some way, shape, or form on the ImageNet dataset. They're very good at the general task of recognizing images. Our final layer has a bunch of random weights. It's not good at anything. So we expect that we need to change that final layer quite a bit more than we need to change those other layers. So we can explore this a little bit. What we want to do is train that final layer without doing any damage to the weights in the rest of the model. And the process that Fast.ai has for handling this is that it starts out by freezing all of the non-final layers. So if you train a single cycle, you do the train one cycle function, it's not going to affect all of the layers that were trained over the whole course of training the ResNet model. It's only going to train that new final linear layer. And we can look at which layers are frozen or not using the learn.summary method. So we have all of our layers here, and trainable is false. It means that the layer is frozen. Now, I noticed, and I'm sure you'll notice, that the batch norm layers, it shows true as in trainable, not frozen. I don't really know what this means. There was a discussion on the Fast.ai discourse about it that I did not get too deeply into. I would call that an open question for myself to figure out. If anybody else knows right now, feel free to chime in.
Probably just to add, batch norms are things that kind of like improve the performance of the model. So for now, it's covered actually in the book, so don't worry about it. But it's not in the current set of lectures, unfortunately. So okay. It's in the, I think, chapter 14, which is no longer covered by the lectures, but just a short. It's just to improve the performance of the model, so it improves your accuracy. Think of it that way for now.
Got it.
I do notice that there's a small number of parameters. Maybe it doesn't hurt performance either because it has such a small number of parameters.
Yeah, that's another reason. It's not a big
normalization is usually pretty straightforward stuff. Not much.
Yeah.
You know, it's just normalization. It's not like convolutions.
Yeah. Just for now, think of it as something that's like improves the performance of the model. That's a characteristic of the architecture that we're using, Resnet. So it uses batch norm. So think of it that way. But it'll be covered in chapter 14 in the book, if you want it.
So the key point from all of this as we scroll down is that our final linear layer here is trainable. So when we do fit one cycle, we'll be making changes to that final linear layer. I'll put this on the GitHub repo that I put up, and I linked to the discussion about batch norm, but I'll look into that a bit further. So we're going to proceed to that step I mentioned, where we're going to train those random weights to actually not be random and to fit with the problem at hand. So to do that, we use the fit one cycle method of our learner. Do that for 3 epochs, and I just use the max learning rate from the book there. I didn't go much into learning rate on this guide through, so we won't worry about that. And just 3 epochs of training that final linear layer, and we get our accuracy from that initial accuracy of little less than 60% up to 95%. So that's a huge change, and I think that really illustrates some of the power of transfer learning. You know, I did this for free on Colab, 1.5 minutes, and we're able to fairly accurately discriminate among those 20 different classes. So the next step, we want to see if we can do a little bit better by fine-tuning the rest of the layers of the model, those ones that were previously frozen. So to get at those, we are going to use learn.unfreeze. And you'll see that the layers that were previously frozen are now unfrozen, except for the ReLU layers, which don't have parameters to train anyway, so we wouldn't expect anything there. And our linear layer is still also trainable unfrozen, so that will still be going through some level of updates. I did do the learning rate finder here, but again, I'm not too worried about the learning rate in this particular notebook. So next we do the fit one cycle again, which now that those layers are unfrozen, we will be fine-tuning all of those layers. And we get up our accuracy by another percentage point, a bit over 96%. And of course, we can do all of this using the fine-tune method without having to worry about manually doing learn one cycle and freezing and unfreezing. So to do that, I reinitialize the model, specify the threshold of 0.5, and go to read through chapter 6 for all of that. And then learn that fine tune, I say 6 epochs and 3 freeze epochs equals 3. This does exactly what I did before, which is to say it trains only the head of the model for 3 epochs, and then it does another 6 training the full model. And again, we get up to that 96.2% accuracy. Yeah, and that method that we went over in chapter 5 on the single label problem translated pretty much seamlessly to the multi-label setting of chapter 6, really showing what transfer learning can do and how easy it is to implement using Fast.ai. So that is what I wanted to go through today. Any questions or comments or discussion?
No, that was good. Perfect.
I think Daniel's ahead of me.
No.
All right.
I think for me, I've been trying to do something more or less like this for all of the chapters where I, at this point, don't look at the pre-made notebooks at all. I try to just actually type everything out myself with a slight variation if possible. Mm-hmm. And I think that's what's really been helpful for learning this material.
Yep. That's great. Thank you for that.
Yeah. Then I'll stop sharing.
All right, Anya, are you ready? Let me make you co-host.
Yeah, so as I expected, Daniel's was pretty good and mine won't be, so just setting expectations there, it's a disclaimer. I do agree with Daniel that I also wanted to do something different than just running the clean notebook, because when I run it, everything works, right? Even if I go step cell by cell, it still works. But what I tried to do, let me share. So let me know when you can see my notebook.
We can see it.
Okay, so what I tried to do, I tried to go through chapter 5, which is image classification, not chapter 6, which is multi-label, but chapter 5 is multi-class classification. And I tried to do the same stuff with MNIST. So MNIST is a full data set with 10 digits. In chapter 4, we did just 307, which is binary classification, and MNIST is multi-class with 10 digits. So first of all, I'm using GCP. I really like it, but every time I restart, I have to do all of this on tar again. So I decided to pickle my data so I don't waste my money. So first time, if I do it first time, I go through loading and everything. But if I do it after I already saved my data loaders, then I just grab it from my local directory. So that's just a saver of loading data. I don't want to deal with it every time. And the way I did it, I just have this flag. If it's true, basically, I set it to true after I save the data, and after that, I just don't deal with it. And at that point, I just come in. Basically, I save my data loaders into digits train set and digits test set. Does that make sense why I did it? And it's really not important, but it's just for saving code chunks. And the reason, so what I wanted to do, and I haven't quite finished, I wanted to do it the way I do it in real life. So we have train set, and this is where we train the model, and then later we measure performance on the test set. And the test set is something that I don't touch at all. I don't use it for validation. The way I get the validation set is from the train set itself, right? Because we have this random splitter, which splits my train data set into 20% validation data set and 80% train data set, which we train on. So I could have used test data set as a validation, but this is not recommended in real life because test set should never be touched. And the actual performance on test set matters more than fitting to the validation data set. So that's why I decided to do it different. Any questions about that?
No.
Okay.
And I noticed you just did one transform, just a resize. Is that?
Yeah, I didn't do augmentation with the MNIST because MNIST is pretty standard and pretty simple. So it's not like, you know, cats, you have to turn them upside down to figure out if it's a cat.
I see. They're all kind of oriented in the right way.
Yeah. It's already standardized. It's already, you know, black background with white digits. So I didn't worry about transformation. Okay. I just wanted to resize to make them the same size standard. So pretty much, you know, data blocks and data loaders like in Daniel's example. And I always try to keep track of classes and shapes because if I know what class it is, it helps me understand how to deal with it. And shapes, you know, if shapes don't match, then nothing works. And in my case, I didn't finish because nothing works, but that's what I'm sharing.
Yeah, exactly.
Yeah, so this is where I'm saving my data loaders to a pickle. So later, you know, next time I come to Google Cloud, I don't go through all of that building data blocks, I just load them. So I'm checking my data block, it looks good, you know, that's what our digits look like. And I'm gonna do it backwards. I'm gonna do it the easy way first. So I'm gonna use the, sorry, I thought I did it backwards, but no, I did fit one cycle, but pretty much one cycle what I'm trying to do, I'm trying to look at the results with pre-trained model and without pre-trained model. So here I use Resnet 34 network architecture. I'm just not using the results. So by saying false, I'm training MNIST myself, and this is pretty standard, just one cycle, fast, and learning rate is as in our examples from earlier chapters. And the thing is, what's surprising is that the error rate is already pretty small, right? So even without pre-trained network out there, it's already doing pretty good. So that's a mystery to me. I'm glad everything works. And then I go through the same examples as in the book. I look at one batch, I look at the outcomes, then so this is the Y in the train set. So this is the label in our batch. So we have 256 digits, and the first one is 5, and this is the labels. And then I'm looking at my prediction, just the first one, and this is that tensor. Because we have 10 digits, I'm getting a tensor with the shape of 10. And the way we know it's the right answer is where it's the maximum number. So if we go look at everything, this is the maximum, right? So, and this is the prediction, which is 0, 1, 2, 3, 4, 5. So this is correct. It predicted to be 5, and we know this is a 5, so I was happy to see that. And I always make sure everything adds up. So, the point in the book was about all of that softmax and cross entropy that makes it conveniently for us to add up to 1. If it doesn't add up to 1, then it's not cross entropy. That means we didn't finish converting it to adding up to 1. Okay, so then I just looked at the loss function. It's pretty good. And model interpretation is, we're looking at so first I looked at the top losses. So 5 examples where we mispredicted. So this is really, it predicted to be 1, but it's actually 3. With these, like, I have no idea why this is like, how did it predict to be 1? Yeah, so I'm actually kind of confused, because here this looks like it's possibly a 9, and here it looks like it's, it could be 5. This is actual is a 1, but it's a strange, really like a fat 1. So maybe, I don't know, maybe if I rerun this again, and I'm just showing it in GitHub, so this is static, I can't rerun it. So maybe something didn't go right there. But this is pretty much that not using pre-trained architecture, and this is the confusion matrix, and we're looking at mostly confused, and it's just showing you that, like here, where actual is a 9, it got mispredicted 12 times. Mm-hmm. And it's actually a 4. So this is just, stepping through the same examples and seeing where it's mostly confused. So it's like here and here, 6s and 9s are more confused and like 5s are easier confused. So that makes sense, at least to me. So then I tried to do the same stuff, but now I did use the pre-trained model, the same Resnet 34. And I find, this is where I did it the easy way, because I used the fine tune. and fine-tune does everything for us, so we don't have to worry about anything. So this is what it was on the first run of first. Sorry, I can't even like, I'm blanking out what I want. Like, I know in my head what it is, but I can't put a word on it. But basically, this is our initial error rate, and then by fine tuning, we're improving it, and it looks much better, right? The error rate is decreased significantly. This is a good decrease, and it, like on GCP, on Google Cloud Platform, this is how much it takes, because MNIST is a pretty large data set. And then I'm doing the same thing, predictions, and just checking it out, and the same, looking at the confusion matrix. It's now I set it to minimum of 4 errors, and you can see the numbers here are way smaller. We don't see 12s anymore. We don't see 9. So it's like once or twice it messes up. Like here, it messed up 3 times. So it looks like it's doing much better. And the only difference was that I use a pre-trained architecture, network architecture, and I fine-tuned twice, right? So very sizable improvement. And then so now with this fine-tune, everything magically works, and I'm happy it does, because like I will probably never will go through this under the hood again, because it's really hard. So in the book, it was about improving our model. So the idea is, if our learning rate is too high, we start diverging, which, you know, doesn't help us with finding a better model. And if our rate is too low, then it takes forever to train. So I try to set up my rates really, really high, and it still performed really well. So I could not make it happen. This is where it's the difference between the clean notebook and my, you know, whatever I'm trying separately. I tried just like 0.1, I tried 1, I tried 5, 10, and it still does pretty good with fine tune, even just one fine tune. So I gave up because I spent too much time on that already. But the idea is that we want to use, like, how do we find what this rate should be, right? Because we're supposed to provide this value. And in Daniel's example, he used the book. I used the book too, but then I wanted to like try to diverge from the book, do it a little different. So according to the lecture and the research by Leslie Smith, it's somewhere like this is the minimum, this is where it's the steepest. So I kind of get from the chapter that we should use the steepest, but then the rule of thumb is using the minimum minus divided by 10. So if it's not here, then it's somewhere here. And because it's a logarithmic scale, that's basically, I couldn't figure out how we chose this value. Like, I watched the videos, I read the book, I did the notebook, and I still like don't understand how to do it. So I looked online and I found
Can you point on the chart where 3.63 times 10 to the minus 3 is?
That's a good question. I wish he had a red dot where it is, because
well, we can figure that out, right? So if it was 1 times 10 to the minus 3, it would be right there.
Yeah, correct, right? So it must be somewhere here, right?
Let's see, is that right? Yeah, it would be roughly a third of the way to the next one.
Yeah, so I mean, conceptually I understand it, but I just couldn't come up with this number myself, and like I pretty much spent all my time on this.
I would almost posit that it doesn't matter. Anywhere in that steep spot is going to work almost as well as any other number, right?
Yeah, I agree. It just I made sure I watched the video, and it just Jeremy, to him it looked so simple why he got this number, and I'm kind of like, I'm still lost. So I just wanted to see what other people are doing. So I found a reference, like there is a guy out there, and I posted in our Slack channel. He created his own finder of this number. And this is the function that I have at the very, very, very beginning. I always put global variables and functions in front. So this is his code, and this is the link, and it is available in our chat if anybody has time to spend on this. I actually don't recommend it because it's a lot of time wasted. Depending on your goals, because we already have that wonderful, fine tune and everything works. But yeah, pretty much what I did, I tried to use his function. It gave me this plot. I really appreciate that he has these red dots. I really don't know what this means. I do understand what it means here. I kind of see it's in the middle of that slope. But basically it gave me this number. Using that function, like you can do it without the plot or you can do it with the plot. Here, I used it without the plot. It gave me this number and the same number when I used it with the plot. So I tried to put this number in here. And I trained with this number, and this is what I'm talking about. The error rate is already pretty good, and then it gets smaller and smaller. And I tried to do by the rule of thumb, where it's the minimum divided by 10, which is about this number. So, they're pretty similar. So I agree with Dave's comment that as long as it's somewhere along, as long as it's away from the minimum divided by 10 and somewhere like in the middle of that slope,
go for it.
Yeah, just go for it. Don't waste your time because it just doesn't pay off. So, and then I just wanted to know how it works under the hood, and Daniel covered this already really well, so I'm glad he did. That's why I wanted him to go first. But it's pretty much like, it's you set this CNN learner. It does fit one cycle. By default, it freezes everything that's pre-trained, and then we can fit, I think by default it fits once, but we can provide how many times we want to fit for our data layer, where in my case it's 10 possible digits. Resnet 34 has way more and I only have 10. And then so it freezes by default, then we do this fitting, and then it unfreezes, and everything works better. And I followed Jeremy's recommendation to look at the better rate again and find LR, use this LR find method. And in our book and in our clean, everything looks beautiful and smooth. This is what I got, which, nothing like the book example. So go figure what this means. I just looked at it in amusement and moved on. And then I tried fitting 6 layers, and this is where he was saying that at some point, so here we used, we were supposed to derive a better learning rate. I just used a smaller value, just because I can. And then I tried to fit 6 more cycles or epochs. And, it was kind of like did a little bit better, but then worse, then a little bit better, then stayed the same, then a little bit worse and a little bit worse. So I determined by epoch 3 or 4, it should do pretty well. And I think I meant to run it. Or no. So yeah, so I determined that, and Jeremy recommends to rerun it, but you know, I'm already short on time, so I'm like, I believe him, I'm gonna stop here if I really train it. And here, then later he recommended to use this slice where we provide beginning and end, and depending on the number of fitting, so here 6, so it would split it into 6 equal ranges, I believe, and this is how it performs there too. So you could see that it did pretty well. It went down and down and down, and I stopped at 6 because it was good enough. And this is what my plot looks like. So not as smooth as in the book, but you know, it gives you the idea that the train is kind of stable. Oh, sorry, the train validation performance was kind of stable, and train was all over the map. And then I ran this because it's in the book, and this is just using a deeper architecture because now we have 50 layers, and I wanted to try this reducing the precision. And it did, the beauty of this, that with the reduced precision, it performs faster. And because we have more layers, but it's lower precision, it's still faster than Res 34. You know, it took longer here because the precision was twice as big. So this is where I stopped. And the conclusion is that deeper doesn't always mean better. Use your judgment. So if you see something like this and crazy charts like this, then maybe something is not working. Maybe just stick to fine tune and look at everything working and don't try to figure it out.
Why was that chart only between those 2 points? Normally they're like between 1 times 10 to the minus 8 and 1 times 10 to the to 0.
Are you looking at this?
No, actually the one above, that right there. That's you've got it zoomed in to a very small portion of that learning rate curve.
Yeah, you're right. I just use the whatever default, and for some reason that's what it decided to zoom in. I guess it's because the minimum and steep is at those 2 points. You see how it suggested? And yeah, you're right. Normally, and I didn't want to go inside of this function and modify it.
I don't blame you.
Because that would give me, like, I would have to give up this course to figure it out. But yeah, this is why, because it's kind of using these values. Yeah. And so that's my conclusion. Use your judgment. Things work beautifully in the book, but it's much harder to figure it out. What I actually wanted to do is evaluate models on the test set, because remember, I saved my test set. I didn't use it for validation, and I wanted to check how my pre-trained, not pre-trained, and this funky stuff worked on the test set, but I couldn't figure it out really fast. I got on chat, I agreed to show my results like within 3 hours before this meeting, so I couldn't figure it out. And
it's really funny. Before you joined the chat, I brought that up. I was trying to do the same thing with Pascal, and I also couldn't get it figured out. So
yeah, and I couldn't figure it out because I can't. I do this for a living. I do this. I train models at work, and I'm used to the framework of scikit-learn where everything is super easy. There's train and test split, and validation happens by cross-validation. You split the train data set inside and you cross-validate many times. That's how it happens. to find a better rate, we use grid search. With the grid search, I can figure out which, I provide like 10 values for learning rates, and with grid search, I find a better one. There is also random search approach. So I'm very used to choosing like test set and measuring performance on test set. And usually it's pretty simple. I do like a prediction. I make sure it's the same list. If my labels are in a list, and my test results are like test predictions are also in the list, and it's super easy to compare. What I couldn't do here, I couldn't just deal between tensors and lists, and this is where I got stuck, and I may figure it out, I may not figure it out, because I need to move on too. I can't dwell on things. So
we're all learning that.
Yeah, so that's what I'm sharing, and sorry I don't have
That's great. That's excellent. So the idea in this next step would be to apply the models that you've trained above
Correct.
to the test data that you have pulled out before. Okay.
Yeah, because I'm saving, so this crazy one I'm saving as a learn, but previous ones I'm saving as my learn and my learn one. Okay. So I don't have to rerun them again. I can just predict on this my
use
learn.
It. Right,
yeah.
right.
Yeah, and I wanted to compare the results, and that would be, the final, like, here we go, this is how it works, and here we go, I don't know how it works.
Yeah. So your test set has labels, I guess? Yeah.
Yes. I did figure out, I did go as far, I just didn't submit it to Git yet. I did figure out, you get your test set, it comes with the image and a label, right? So it comes with tuples of images and labels. Right. And then labels are given as, 6, 9, 5. But my predictions are, by using the model, I get that tensor of 10. And I do that argmax where I find the highest value, and that's my answer.
Yep.
And that's where I couldn't just convert from that final tensor, because it's still a tensor, and I couldn't compare it to a list, and that's where I got stuck.
You were close. You're very close. So the argmax of a tensor is still a tensor. I would think it would return the index into the array.
So it already, argmax already gives, so basically I use argmax, which returns an index, and then I use the value. So I did derive that the value is 6, for example.
Okay, you're getting closer. I can tell. Yeah.
But no cigar.
That's true.
Yeah, right.
So you put in a learning rate of 10 at one point, and it still worked just fine.
Yes.
That's what really jumped out to me. Like
that's not right.
It's interesting. That's one of the things. I pulled up the source of fine tune, and I guess if you really wanted to isolate the learning rate and see what happens, maybe you'd set the LR mults parameter to 1, so it's not doing anything adaptive over the course of. But still, I would imagine that starting with a base learning rate of 10 would make it crazy no matter what.
Yeah, that's what I expected. And, I expected it to even start diverging at 1, because, 1 is pretty high. And it didn't. And I'm like 10, and it doesn't. So I'm
1 is not just high. It can't be 1, right? I mean, isn't the learning rate the portion of the step that it's going to use? And if you put in 10, it's going to go like 10 times.
Correct. So I don't know. Like, if somebody knows, please speak up.
Is it because we're using pre-trained models? And you're like Resnet 34 and 50, and they're already kind of done for you.
Yeah,
so no matter what you put, right?
Correct.
You're going to get a 90-something accuracy, right?
Correct.
Even if you screw up the numbers, it's because you're using a pre-trained model. Now, what would be interesting is if you didn't use a pre-trained model and you just went, you just created your own convolutional network and you just started putting, these layers in there, similar to, maybe Resnet 34 or something.
Yeah.
and then see what happens with that learning rate, because I'm pretty
Oh,
sure.
I'm sure it would diverge like even at 1.
Yeah.
Because remember last week I did I showed you guys about how, you know, I did that 3 or 7, and I did no, I did the roller coaster, and how I used Jeremy's example with the 20 points with the roller coaster, and that's where I manually was fine-tuning these rates, and I did see immediately, like if the rate was larger, it was diverging like crazy. So I did go through manual, but it's easy with 20 points. I can, you know, see everything and look into everything. I just couldn't do it here, which is a learning lesson. And I would say don't try it at home.
And my other question, which I also ran into with mine, hopefully a dumb question and I'm missing something obvious, but for the recorder plot loss, what is the x-axis there? Like, I know it's some measure of time and running multiple epochs, but I couldn't figure that out on mine either. Like, the y-axis is the loss.
I think it's batches, right? Batch by batch.
Yeah. Yeah. So the x-axis is the, you know how you run, let's say, 10 epochs, right? And you have, let's say, a batch size of 64. Yeah. So for each epoch, you have something like divide the total number of samples by the batch size. That's the number of batches.
Yeah.
So the x-axis is multiply the number of batches per epoch times the number of epochs that you have, and that's basically the. So
yeah.
Got it. That makes sense. Thank you. That was driving me nuts. I couldn't figure out what
total number.
Label your axes.
I'm trying to look. Sorry. I was like trying to look for an example for the. I couldn't find. I have an example where you. And actually, if you search through the forums, there's an example somewhere. I know there was an example because that's where I copied it from. But there's an example of using a test data loader separate. So you're so in your case, Anya, you were using the training set and separating using a random splitter, right? And then holding out the what
I'm holding out the test set, right?
Test set for the final, just for the statistics. I'm gonna look for it and then just probably post it in the Slack channel. But there's an example of how to do it.
Yeah, because it's intuitively very easy, right? Because all you have to do is compare the results.
Finding an example, because once I found it, it's pretty easy.
Exactly.
The thing there is that you don't need to create a separate data block. So it's going to you will create something called a data loader, because it will load it from a separate folder, usually a separate folder from what they use, right? For the validation or the training set. Or there's even a case, I think in MNIST, I'm not sure, there's a test, I think it's MNIST sample that has a test, a train, and a valid. So there's like 3, and you can use the train and a valid for like the training and validation, and then hold out the test, because I think I remember looking at it and then I couldn't find what the labels were for the test. And that's the way they usually use it for
Kaggle. Yeah.
So they don't give you the labels for the test. You're supposed to submit your test, and then it will give back to you the results.
Correct. Yeah.
Right?
And
So there is, I just need to find an example. So I'll look for it and then post it probably in the Slack. I can't find it right now. So that's one thing. And as for the learning rate, Dave pointed out something about, as long as you can find that steep slope, the performance will usually go down to that a very high level. The thing that I'd like to raise is this point where there's actually, you in general, you'll see 2 types of LR find graphs. And that's when before you, like when you first like do create the learner and the layers are frozen, if you try to run a LR Finder, you'll see something like that. The one that Anya is showing right now, where there's a very clear steep slope down to usually something like 10 to the minus 1 or 10 to the, it depends on what data set. But there's usually a very steep slope that you can find
early on.
Then it rises up slowly at the so it's very easy to find what the learning rate to use, right? So anytime if I can see this, automatically my mind would go, let's try 10 to the minus 2.
Yeah.
Right? So that's easy. That's the one that's easy to like find the learning rate. There's another kind of learning rate where I'm not sure. I don't have a sample.
I think it was after one cycle.
The slope is it's almost flat.
Yeah.
It's almost flat in the range of 10 to the minus 7. And then at some point it will go up. And that means it's just too high now. And the other thing is show the one that's like the weird stuff, the one with the weird learning rate. That usually it's kind of something like this. This is where it gets weird. And it's like, this is where the learning rate, picking the right learning rate becomes more critical because it's much harder to pick which one to choose, right?
Yeah.
And in this case, my guess would be, something very low. And that usually means, and this is usually after you've done training and it's getting to that point where, I've gotten good at because if you notice the loss and the ranges are actually, you're right, it looks for the steep and the min.
Yeah.
So it's that range. And so it doesn't cover the same stuff because it's like the range of values, if it's too high, it doesn't get into the graph. So you'll notice that, like in this case, if I train at something like, I guess something like 2 to the 10 to the minus 7, or even something like 0.5 10 to the minus 7, something like that. That's what I would try, is find the steepest part, and that's the one that I would use.
Yeah.
And that's for the this is for the, what you call this, the low part, because you when you run the slice and your LR max is just 1 digit, it's actually gonna use a default range of values. It's still gonna use a different rate for the it's gonna use the code is this. It's like, if you give me a single number for the LR max, I'm gonna do the what do you call this? The ranges, because it's usually for Resnets, they're usually split into 3 groups. So there's gonna be 3 rates for these 3 groups. The one with the smallest one is the one for the ones that are like the lower layers.
Later, yeah.
And then the highest one, is the one that's for the one that we just added, the one with the random. So those are the 3 groups.
Do they break those into linear divisions? Even thirds, or
I can't remember what the ratio is. But the one that's where you have finer control over that is if you pass a slice to LR max. That's the one with the slice, and then you have 2 numbers.
Yeah, I did
That's
that.
What they use there is, I remember they're using something called a geometric progression. So it uses the lowest one for the first one, and then the top one, and then in the middle, I think they use a value. It's not exactly half. It's
right.
like logarithmic something. I'm
Yeah.
trying to remember, but the point is, it does that. So the one where you press the slice, and it used to be that I remember Jeremy was saying, well, when you run fit one cycle initially, it uses a default learning rate of 1 to the -3, I think, by default. So what they usually do this the second time around, just divide that by 10 and use that for the the top layer, and then use the 1 - 6 to like find the level where it's not yet, it's far from the steepest, but not so low that there's no improvement.
Right.
The point being that once you get it to a high level, it's easy to get it started. That's why, if you notice, fine tune, you don't even specify a learning rate.
Correct. Yes.
Because it's so easy to get it to a high rate. But it's when you get to that high rate and you want to improve it further, that you have to like take a look at LR find, analyze what, and sometimes there at that point, which I didn't notice that you're doing is, you might want to, like, if I run something and then it gets to a good rate, but I want to improve it, I usually run a save, a learn.save to save the model.
I see. Okay.
So that if, for example, the next run, I do something that screws it up, I can always reload that previous model that improved and then try to like experiment further.
So I don't have to restart it.
So instead of, I noticed that you're saving the data loaders, and normally I don't do that because they don't take much time. The data loaders itself, building the data loaders, if you notice, they don't take that much time. The one that takes time is building the models, and that's the one that you want to save midway through. So like you're experimenting, playing around with it, and you get to a good high rate, like, oh, it's 0.0045, and that's the best one yet. So I might want to say, I'll save that. So learn.save, it puts it in a folder on models. And then play with it further, experiment, try to improve it. And if you get worse and you want to like roll it back, you can just load the previous highest model that you have.
Yep. Sounds good.
Yeah, so that's the other thing. And then, yeah, the fact that you're using plot loss is good, because once you get to that level where the valid is kind of flat, I think that's probably the best that you can do. It's still good though that your training loss is going down. So my suggestion is to try to experiment. I mean, save the model at that point and then see if, because normally they kind of follow each other. So if your training loss is still going down, after a while, the validation loss will also go down a little bit more. But if I see that the validation loss starts going up, then that means I'm close to overfitting, and I might not want to like do that.
Yep, makes sense. Yep.
So here it's like it's almost flat, or it's even lower in the earlier parts. And if you notice, the last point I'd like to raise is we're using fit one cycle, right?
Here, yes, because we're looking under the hood.
Yeah. No, but we almost always use fit one cycle. And it's like the thing with fit one cycle is that it uses different learning rates along different parts of the training. If you're thinking of the batches times the epochs, at the start, it has a low learning rate. And then in the middle, it increases it. And then at the end, it kind of slows it down. That's why there's another one, I think, LR plot, LR find, recorded that LR find, where it, and then you can say moms equals true. I don't know if you have it here, but it kind of shows you the change in the rates.
Yeah, there's so many tricks.
Yeah, but what I'm saying is those are the things that like you might find that the best rate is in the middle.
Yes.
Like, but when you try to reduce the plot, you say, I'll rerun it again on the old model. I'll roll it back, run it again. It still won't be the same because it'll apply a different shape for when you're running it. It might not always apply. So that's why it's like if you're getting to that point where the accuracy is already pretty high or as high as it can get, because it depends. Like there are some data sets where you just can't get something high enough.
Yep.
Well, at what point would you start to entertain using a different optimizer or different transforms to try to improve?
The thing is, it's like for me, you're looking at a simple data set like the standard stuff that we use, and we're just playing around. It's usually just to run fine tune first, right? And then run an LR find, and then fit one cycle and experiment and play around and try to. I always watch the plot loss to see whether my validation loss is still going down. If my validation loss is still going down, that means I can train on that same model further to see if it'll go down even further.
I see.
And then later on, I think they covered it at the end of the lecture, where Jeremy starts talking about things like regularization.
Yep.
Yeah, so those are additional stuff. But for me, the basic go-to stuff is just run fine-tune, or even fine-tune, and I probably would increase the number of freeze epochs, because that's the one where it trains it on the untrained, on the random part first, and usually it might be enough for just one before I train the whole thing, or I might run it for 3 or 4 before I run it for the unfrozen, the whole model unfrozen with like 3 or 4. So it kind of is like an experiment, and it's gonna be different for each data set. So it depends.
Yep. Yeah, this was a fun exercise.
Yeah, and the thing is, I guess one of the things that Jeremy always emphasizes is, don't just learn the theoreticals, always try to apply it. So I think it's good that you're figuring out, and then you get to the point where I don't know anymore. Jeremy would all say, that's when you experiment. That's when you like play around with it. And hopefully by that point, you've gotten good results.
Yeah.
I was like surprised that I was like running on this data set, on the pets data set, and getting something like 94. And then you go to like this site called Papers with Code, and it turns out the best record they have is around 96, 97 for the pets data set. So 94 is like, wow, that's like 3 points within, and then just playing around.
Yep.
And in real life, I mean, those 3 percentage points probably wouldn't mean a thing. So in terms of getting something useful, those 3 percentage points would probably not make much of a difference.
Well,
so that's pretty good.
Tell that to my cat that was misidentified as a dog.
Yeah, but the thing is, that might mean that even the best ones aren't good at that.
Right.
That's
Yeah, all the difference, yes.
Yeah.
all right. I think I've shared enough. Any other questions before I stop?
Thank you very much for that.
Example, sorry.
Yep. So you did actually go with a deeper network with lower precision, and made it faster. It got just as good but faster.
Yep.
Okay, that's good. That's
and that's the lesson. Kind of just use fine tune. Try to see, if more layers and less precision gives you better results, and you're saving time and
Or quicker, yes.
yep.
Yeah.
So,
Another note, Anya, I noticed that you're using the resize to 128.
uh-huh.
The thing to notice is that in MNIST, the actual size of the
Only 24.
images are 28 by 28.
28,
Oh,
yeah.
that's a good point. Yeah.
So increasing it to a bigger size doesn't really help. And at
I
least
was wondering why they were looking bigger.
for
You're
MNIST,
getting
yeah,
more.
at least for MNIST, it doesn't matter. But for like
Okay.
something like the pets data set, it does matter.
Correct. Yeah.
And there's a chapter that we didn't cover called, it's chapter 7, in case you're wondering. In there, they discuss a technique called progressive resizing,
Uh-huh.
where like on the pets data set, you might start out with a small, you start out with small sets with small sizes for the images. And then once you've gotten it to a good point, you're gonna use that, something like your own version of transfer learning, where you're gonna rebuild the same, you're gonna run the same model that you've already pre-trained on a small sized
Oh, neat.
images on the
Mhm.
same data set, but this time around you
Higher-
resize it to something bigger.
Higher
So it's called
resolution.
progressive resizing.
That's
Uh-huh.
interesting. So
And
it
that
starts
usually
out,
improves it. And then, especially on large data sets. So I guess something like
Mm.
what RK is doing. I remember his previous thing with the large sized images for his cars.
Mm-hmm.
So
Yes.
one thing if you want to speed up training, is to try to experiment with building smaller
first.
sized images first,
That's
so
a
that
good
we can
idea.
build
Yeah.
a good pre-trained model, and then rerun it again on slightly larger sizes, and then probably run it again on the largest size last, because by that point your model has gotten good at like looking at the same data set, so it's not going to overfit because it's looking at the same data set but in different sizes, so it's like a kind of a data augmentation.
Mm-hmm.
where is that progression happening? When you change from, say, low resolution to high resolution, where in the cycle is that happening?
No, you just rerun it again, change the data loader. So you read, so
You
in your data
freeze,
block,
you do the whole, like,
trying it
unfreeze?
first, as well as to how like fine tune,
Oh,
run
okay.
LR find, and then get it to a good point for that, what do you call this, for that, for that, for
Data
your data
set.
set for that particular size.
Yeah.
And then you go back to the data block, change
Change it.
the item transforms to use a larger size image. So you might start out with something like 128, and then I'll try 224. And if my real image size was something like 299 or for something, so the second time around, I'll rerun it on like 224, and then plug it into the DLS. So I changed, I still have the same model. I just assign the DLS to my new DLS, which has the resized thing. And then I rerun the model again. And that will usually improve the model further, because now it can see the finer details and distinguish between them. And then again, once I get to a point where it's like flattening out, I'll retry it again on. And that way, because you're usually starting the training on smaller images, it'll run much faster. By the time that you full-sized images, it gets slower and slower.
Right. So that's
your time on that.
Does that go faster than if you just started with a big image at the beginning?
Yeah, usually because if you have like large images, it's usually training slowly.
Sure.
Hard.
The convolutions take forever.
Yeah.
To work through those big images.
Yeah. So that's a technique that's discussed in the.
Cool.
It used to be, I think, in the previous years lectures they covered it, but this time around he didn't cover it. even though it's a chapter in the book.
Okay.
Yeah.
Very good. That's nice. Good thoughts.
Hey guys, our new member or joiner, Henrique, is that your name? Yeah, you're on mute.
Yeah, that's right.
Okay, he has a question he'd like to share and share the screen.
Yeah, let me. I don't know which monitor this is. Oh, hold on. Mac system preferences. I might have to close Zoom. Let's see. Yeah, Zoom needs to restart. Give me 1 second. Sorry about that.
Now it's just silence.
I know, yeah. But,
Oh, here it comes. Admit. And co-host.
All right, there we go. Everything's good now. Yeah, sorry. Mac has system preferences that you need to fix. Okay. So I was doing the minutes data set from last week's, the lesson 4. And so originally my question was,
Can you increase the font a little bit?
yes. Is that better?
Yeah.
Okay. So originally my question was, why did we go through all of this instead of just using ResNet? So I just found out that this was creating our own neural network and our own model, whereas like using ResNet was taking this pre-trained model where it had its own neural network. So that's why we didn't have to do this with the ResNet example. So I guess my question is, does anyone have the CNN version of the MNIST data set that I can look at for this problem set?
Or make your own?
Yeah.
like what is the actual layer by layer CNNs?
Yeah, so I guess like how can we go about like creating our own CNN from scratch, not using a pre-trained model? So like, yeah, does anyone have anything like that we can create?
Wasn't there that summary function that would expose each layer? Was Anya in that thing that you or was it Daniel?
No, I think it's
Daniel,
Daniel, yeah.
Yeah, there is that, and also chapter 14, Resnets, is, I think, on the topic of making a ResNet from scratch.
Okay.
Which is,
I think technically that's
considerably more involved than what we've
not
done so far, but yeah.
Well, what would you say?
Layers stay the same size as you go down 64, 64, 64, 64, 64, 64 to 10.
Mm-hmm.
Whereas a CNN would be reducing until it doesn't, and then it'll be increasing back as you add the fully connected layers.
Yeah, this one has the linear layers there. You're going to have convolutional layers before that.
Okay.
And
But
it's like,
I guess it'd be easier if you had some code to look at.
yeah.
And the convolutions themselves have their own behaviors, right? That's exactly what a convolution is.
Yeah, you have pooling and stride. I tried to get Arcada.
Yeah. Well,
give us a small demo on that, but he's having so much fun on his birthday.
Yeah. Somebody said it was in chapter 14, building one from scratch.
Yeah, Daniel said that.
That's
Okay.
the one where
We'll get there.
Chapter 13 is the one where it's convolutions.
Yep.
So if you just want to study convolutions themselves, chapter 13 is where they discuss what's a convolution and how it's applied.
And if you look at Chris's notes, did you see the guy who piped into the chat?
Yeah.
His notes. Oh my God,
Amazing.
300 pages of handwritten notes. I guarantee on page like 204 is going to be Andrew Ng's explanation of the convolutions.
This was on the Slack itself?
Yeah, it's amazing. I'm just making that up about exactly what page, but
but it's handwritten notes on this stuff.
hundreds of pages.
Okay, I'll
And he
look.
has it all indexed.
And that's the Chris Maxwell.
Yep.
Yeah,
Okay,
just
I'll
click
take a
on
look
that.
at that.
Click on that link, and as soon as I did, I'm like, oh, come on, what the heck? Oh my God. I looked at it, and
Can one of you guys do that for the Fast.ai videos?
He was supposed to present. Where is he?
yeah, we scared him off.
So my next question is: has anyone tried to apply what you guys have learned to a Kaggle data set?
Not yet.
Hey, Butch.
Not yet.
I've done a couple just from other classes that I've taken, and
Yeah.
it usually where, at least in my experience, where you get gummed up is like they have a very specific submission method. So like whatever they want their loss or their metrics to be of how they're going to judge it, and you have to implement that math, and it's something that's different than like what we're seeing here, and it's like one more layer of like stuff to do, you know. And so like the MNIST one, if you look at it, it's just like it's a ongoing, and that one's pretty straightforward to submit to. But some of the other ones are, at least from my limited experience, were pretty difficult to submit to.
There's actually a set of notebooks. I think in the I'll probably post it in the Slack. But there's one where you can you get the data. It's called the Planet data set. It's like satellite pictures of, and the idea there is, if you want to find the your results, your test, because that's where they have the set of labeled data which you can use for training and validation. But once you've built the model, you're supposed to run it against the test data set where you don't have the labels. But once you have the results of that, you're supposed to submit it to Kaggle, and they'll give back basically your metric based on the competitions. And there is an example there that can show you, and there's already code. There's a package, a Kaggle pip package, where once you approve, it'll like walk you through the whole process of submitting something to Kaggle. So we just need to look for that. But there's definitely like a notebook for that to help you if that's what you want to do.
Well, I was just trying to learn how to, like, the full taking data, inputting it, training a model. So just like the full-fledged machine learning from like scratch, kind of. So that's kind of why I figured Kaggle would be a good start as well after the Fast.ai, and apply what I learned from Fast.ai into Kaggle's.
Yeah, definitely. Yeah, definitely. A lot of people, once they complete the course, go out and try to join Kaggle competitions, either the ongoing ones or even the past ones. Because even in the lectures, like when we go to Tabular, actually Jeremy uses a data set from Kaggle, the one for, I think, Blue Book. It's called the Blue Book data set. So yeah, so definitely when you go through the course, you'll deal with Kaggle data sets at some point. So at least that'll give you clues on how to like build from scratch, from data sets coming from Kaggle, and then building your own models and training them, and then probably even submitting them.
Okay. Yeah, that's what I'm curious about. I mean, I guess when we get closer to chapter 14, I'll try to present them in this.
Yeah,
CNN.
Unfortunately, chapter 13 and 14 is like
We're not.
for that. I was like waiting for.
We'll be done in 2 weeks.
To cover that, and I was hoping that he would, but he stopped there. So you can definitely read it on your own, and if you guys are interested in like continuing the study group after the lectures, that's definitely the next topic that we'll cover.
Yeah.
By the way, it's page 249 in Chris's notes.
Okay. Perfect. I'll take a look at it.
It is exactly what was in that Coursera course by Andrew Ng. He wrote down everything. I'm sure he paused them and wrote them down. And I mean, that took me months. And I didn't even do this. I was struggling with getting the shapes of the CNNs to match.
Even wrote the
Literally.
numbers on the bottom. They're like handwritten. Man.
I'm definitely taking a look at that after this.
Putting us all to shame, I think.
Well, everybody does this once, probably. You know. Somewhere in your life you did this.
Does anyone else have something to present? Otherwise, I'll present my little.
And I can show CNN that I was working on for a different course I was taking, if anybody wants to see that real quick. I can talk about it. I'm definitely not an expert on it, but I understand like kind of the basic concepts of how it goes together.
And you built it from scratch?
Yeah.
Okay.
I mean, it was part of a course, so I followed along building it from scratch.
Yeah. Oh, go for it.
Good enough.
Do you see anything?
Yeah, you're gonna have to increase your font though.
Come on, Anne. Put your glasses on.
What class was this?
You're on mute.
Yeah, I'm sorry. I'm trying to hit the space bar to unmute me, and I'm over on Jupiter, so it's not wanting to. This was Jose Padillo's class on Udemy. It's his PyTorch course.
Oh yeah, I know that one.
Which I think is a really good course. It's completely different than what we're doing because it does everything from the basics of PyTorch. So you don't have any of the shortcut methods or any of the automatic learning rate tuning. You don't have any of that stuff. So it's a little bit different. And so let me see. It's been, well, let's see. 8/16 was the last time I worked on this. Okay. So it's been a minute. But it's kind of the same thing where, you know, it's doing like I think this is just cats and dogs. But here is the basis of the whole network. So this is what I was talking about, where you have these convolutional layers before you have your fully connected linear layers.
Can you increase that size, RK?
I'm sorry. Let's see. Nope.
Just Command plus works.
How's that look?
Good. Yeah.
So I'm trying to remember what all these items are. So you have like kernel sizes. This is the 3 layers of RGB. This is 6 filters that are being applied to this layer. And then this is the kernel size of 3. And then what I think Dave was alluding to was what starts getting tricky is like how you connect these layers to the linear layers. And so I wish I had it pulled up. I didn't get Andy's message about presenting this stuff until about 10 minutes before the meeting started. So I was able to open this file and that was it. But what the key thing here is, so when this layer feeds in, what it's doing is it's taking a 3 by 3 of the pixels of the image, and then it's walking across one pixel at a time. So it reduces the size of the whole image down by the amount that, I almost probably say this wrong, but it's like the difference between what your total width in pixels is and what your filter size and your kernel size is. So that's where we talked, I think in the first class, we talked a little bit about padding, where you actually add black padding around your image to keep it the same size as it goes through these convolutional layers. Because as it goes through these convolutional layers, you lose size because it's averaging. So it's taking a 3x3 of this pixel and it's averaging the values of that RGB.
Maybe
And
not
so,
averaging. That's the magic of some convolutions, is that it can use any function.
yeah. Well, this one in particular was averaging.
Okay.
So yeah, you can do a lot of different things, but so then what's important is because this has the 6 filters, you'll see the next layer has to have the input of 6, and then this one has 16 filters and a kernel of 3. And so what happens when you feed into this linear layer is you have this equation here where the original picture had 224 pixels by 224 pixels. So as you feed this kernel across it, you end up losing 2 pixels.
Right.
And then when you feed it down to this next layer, you end up reducing the number of pixels by a factor of 2. And then because you did another 3x3 kernel, you lost another 2 pixels. And when you're feeding into here, you have to, reduces it again by a factor of 2. And I know I'm not doing a great job of explaining this, but like there's a lot to how all this factors down that maybe I can take some time to put together a reasonable presentation for next week. But what you see is when you do this calculation, what you end up with is 54.5. So then what this layer has to be is 54 by 54. And so there's some more magic that you can do where you force this math to work out to be exactly a whole number, and that has some effects on accuracy as well. I don't understand all that stuff for sure, but so once you have this 54 by 54 by 16 because of the 16 filters here, then this is actually your fully connected layer, and I'm arbitrarily choosing 120 neurons, which means that this 120 output has to feed into this 120 input. And then again, arbitrarily 84 feeds into 84. And then because I'm trying to decide a cat or a dog, I have the 2. So I'm sure that's clear as mud.
And the 6 and 16, those are also just numbers.
Arbitrary.
Yeah. So you can imagine that in the even Resnet 18, there's 18 of those Conv 2D things. So Henry, if you wanna go for that.
Yeah, and so then down here you have the rectified linear levels like what we've been working with, but they also have this max pooling 2D thing, which I'm not comfortable trying to explain exactly what that is. But it's basically a way to connect the ReLU layers together. And then this view part is just the fact that the order of that PyTorch deals with is different than the order that Pandas deals with. I think it's Pandas is, one of them is like rows, columns, and I think PyTorch is like the opposite. It's columns and rows. So you end up having to do these view transforms to get it in the right shape. But then you can see, then there's, for the fully connected layers, there's a ReLU on both as well. And then here's the log softmax that we've been studying.
Cool.
Okay, so Resnet 18 is going to take a minute.
Yeah. The thing is, all these the max pool, the dropout, the batch norms, they're all on chapter 14 in the book. So yeah, it's a little bit more advanced than what was covered in the lectures, but yeah, they're definitely covered. So so the idea is there are all these different layers that try to improve the performance of your model. So yeah, and I think it's pretty hard to like probably.
It's not that complicated, but when you start to apply all these convolutions through the network,
probably convolutions is the one that's harder to understand. Actually, batch norms, max pool,
that might be true.
Easy. I mean, your discusses what they are, it's like, oh, that's all it is.
Right, right.
So it's not that hard.
But taking a 3x3 matrix and reducing it to 1 in the middle, that is conceptually pretty simple.
Yeah.
And that's basically what the convolutions are doing. They're taking 9 pixels and deciding what value to put in the middle one, and then moving over one, taking those 9 pixels, deciding what to put in, and that's all it does.
Yeah.
Which is conceptually simple, but then you start trying to put that into these connected things, and it gets that much more.
The thing that helps me understand is, like, for example, there's 2 things, right? So you have this, in our case code, there's conv2d, and there's 3, 6, 3, 1. And I always look at them as, I think they're called NI, number of features in, number of inputs in. So there's like the 3 channels, which is what you have for an RGB, right? So you always start with 3 because we're using usually images with 3 channels. So it's 3, and then you can output it to an arbitrary number, like maybe 6 or 16 or 64 or whatever. And usually 3 is the standard one. People use 3, kernel size of 3 all the time, and use a stride of 1. So that's like, okay, I move over 3 pixels at a time. My kernel size is 3 by 3, and I move it 1 pixel at a time. Sometimes it's 2, which means I move it to slide it over 2 pixels. So it's kind of like, for me, it's easy to understand. So 3, 6, and then the number of channels for the first layer has to match this next convolutional layer. So it has to be 6 again, and it can be something else as well. What helps me understand like if I am starting to connect it to a fully connected layer, what helps me understand is, you know how there's this thing in learner called summary? There's a method called learner summary. And if you go back to that, you'll see something like a sample in the not in the params. There's like the shape, and it kind of tells you what the what shape the output activations will be. So if you start out with a 28, 3 by 3 by 28, and this is where RK was saying the way PyTorch thinks of the image is something called N. So N is the number of images, so that's your batch size. And then C is the number of channels. And then H is like the height of the image, and then W. So they're usually something like N might be 64, C might be 3, height and W might be 28 by 28 for an MNIST. So that's usually how it looks at it. And then so the 54 by 16 is like, this is starting out with something like, what's the original image size, RK?
It's 224.
So 224, after going through these two convolutions, it reduced it to a size of 54 by 54, and there's like 16 channels up above, right?
Right.
So that's where the 16 is. So 54 times 54, that's going to be the final size. So it's going to resize the whole activation into that. So yeah, so it's going to resize that, and then it's going to retain the -1 actually retains the same batch size. So it's gonna. So the thing for me is like, imagine what the activations are going through. So you start out with an image of 64, let's say 3 channels and 224 by 224, and then once it passes through this first convolution layers, there's a shape to that, and you can like, that's the thing is knowing what the shape should be, and then when it goes through the next convolution layer, it changes shape again, and then you go through this linear, which is actually simpler to visualize. The linear ones are like the simpler ones to visualize. Yeah, because they don't have the height and width anymore. Yeah, so it's just linear layer. So that's the important thing, I guess, is trying to learn what the shapes as the data is flowing, what the activation shapes are of your model. That's the crucial thing to learn. And that will allow you to like create your own architectures.
Well, and like the trick with this is, I don't, probably trick's not the right word, but the tricky part to getting all this to work out is this equation here. Because if you say that you want to start changing this or the stride, you're going to change the result of what is needed here.
Yeah.
Like it's easy to say, well, if I want this to be 16, I'll just make that 16. Like that's the easy part. But the tricky part is like, well, what if I want, you know, a 4x4 kernel instead? Then the padding is going to be different, which is going to change how many pixels I reduce my image by when I get here.
Yeah.
And then when I pool it is where this division by 2 comes in.
There's actually a formula on the chapter, on chapter 13.
I have no idea. This is from, like I said, it's from a different class altogether.
But yeah, I'm trying to bring it up. It's not that complicated.
It's not. Once you.
So I'm just trying to bring up my notebook so that it'll show up. But I'll just copy and paste it into the Slack channel, I guess. But yeah, it's not. It's just a formula. So.
Yeah. Yeah, it's that this number and this number change depending on what your kernel is.
Yep.
And so, like when you're first starting, I'm just kind of warning Henrique that when you get started trying to do this and you say, oh, I don't want 6 filters in a 3x3, I want this other thing, it changes what you have to put in here and here. And so it's not like intuitively obvious, like I just change a couple numbers here and rerun it and see what happens and change a couple numbers. All of the stuff has to flow together. It's all connected. But I have some links to some pretty interesting explanations of this stuff. I didn't have a chance to put it all together today.
Yeah, there's.
So I'll include that with some animations that shows you like how the kernel moves across the pixels, you know, the matrix of pixels and everything. I mean, Jeremy covers some of that too. So
there's lots of examples. I just pasted one in. It's just an article about it, and it shows we're kind of doing this backwards. You know?
Yeah, for sure.
So there's plenty of examples like this. It just gives you the concept of the channels.
I copied the sentence from the chapter. So it kind of gives you, there's a / divide, which means it's an integer thing.
Oh yeah.
So that's the general formula. To get the dimensions of, like, if you start out with 224, so that's n is 224, and then you add 2 times the padding minus the kernel size, which is, in our case, it's usually 3, and the stride might be 1. So that's how, what you end up with.
You can make up your own.
No, this is from the book.
I know. I'm just saying this is.
Yeah. For the architectures, just you play around with it, especially if you're not using pre-trained anyway.
Like for fun, try to create the convolution that would be an edge detector. Just think about what an edge would be on a 3x3 matrix, and you learn kind of the power of the convolutions.
Yeah. But yeah, for now, just think of it as all data flowing through your layers.
Mm-hmm.
All right. Well, if there's not anything else I could help confuse you guys on.
Does anyone else have questions or comments there? I posted also something in a GitHub repo that he does go over manually doing a CNN for you.
Oh, cool.
Thank you.
Anything else from anyone? Well, I would share my stuff that I have, but I think we had enough. Anyone else? How about is it
Sophia Wen?
Yuri, Snow, Sophia? No?
No, thank you.
Okay.
Can you post your stuff to the Slack, Andy, so we can at least take a look at it?
Oh, yes, I will. It's just the 2 notebooks. And what I was going to recommend to Henrique is to take a look at what RK told us to do in the first 1 or 2 lessons, is take a look at the docs. But sometimes the docs aren't matching. And so what I did this time was there's a multi-classification label there. And there's some little docs in there, but I copied out of the notebook that we had for the lesson into there. And I just want to show, don't be afraid to mess around with the notebooks and stuff. And like Daniel said, see if you can just start doing from scratch, right? Just type in everything, and that should get you learning, a lot of the syntaxes. And then when, you're not just shift enter all the time. So eventually you'll start to get it, right? You'll start to hear the same term over and over and over that Jeremy uses. And then, it's just a learning curve, I think, for everybody. And then once you get all the kind of Fast.ai modules and parameters and stuff, I think it becomes easier. So you just have to just keep playing with it every day, and then, just run models, I guess.
Ooh.
All right, well, we're at 7:25, everyone. I guess we will see you next week. Post your stuff on Slack. I don't know when they'll be transitioning us over to Discourse, but we will post away and post questions as well. If you're working on something like Henrique is doing or Daniel's doing, post it up, especially if you get stuck, and let the group kind of help you out, right? Don't be like Anya, just do it forever and ever on one little thing, because you've got like 50 other things to start to learn, right? So don't spend too much time on one little area. You need to space it out, because it's still a lot, I think.
Yeah, I thought the collaborative filtering was a whole new concept. Right?
Yeah.
Latent features that aren't in the data, but come out of the data. That's good stuff. Very interesting and something quite different than what we're used to doing.
Yeah.
Just for reference, the next lesson is finishing chapter 8 and completing chapter 9.
Yes.
So finishing up the collaborative filtering. Well, I think the best part of that is at the end, right? It seems like. I'm still waiting for so much, and I just peeked ahead, and it's like, oh, there it is. It's at the end of chapter 8. Then we only have a few weeks left. Is that?
2 more weeks.
Wow. Okay. So yeah, I guess he was right that this could be a two sections of course, right?
Yeah, he's supposed to do it another
video series.
Another 8 weeks.
Yeah, part 2. But every time somebody asks him, it's like it's like I don't know if he wants to start at any time soon, given the pandemic and all. But
yeah, I suppose you could just go through the book and.
Yeah, but that's what we did. A group of my study group, we continued on afterwards.
Kept going.
And I think it's very helpful.
Does he have clean code for the rest of them? Because I don't have the book. Okay, that might be worth doing.
Those books are all there for the website on the Fast book on GitHub.
I see.
And the questionnaires are there as well. So it's like if you want questions as well to guide you, it's all there. So yeah, definitely can go on.
I'd be up for that.
It helps if there's somebody who's like an expert already, which we did in our class, in my study group. So that we could, like, if we were stuck, we could ask her and say, well, what does this mean? And why is this? And why is that? Yeah.
I mostly get stuck on this stuff that doesn't even have anything to do with.
I know.
You know, it's like like I was trying to convert my car data into multi-class to do multi-classification. And like, all I want to do is show the image, right? So PIL, super easy. IM equals this file. IM show, there's my thing. Okay. Now I can label it. Okay. The 2 car, the 13 car, and the 48 car in this image, write it to a data frame. How do I close that damn window? How do I close the window? Like, I cannot figure out on a Mac how to close the damn window. And it's like I guess to Anya's point, like, it doesn't matter. I can just hit the X. But no, I want my program to close the damn window for me so I don't have to keep going to the mouse. You know, and it's stuff like that. I burn up probably 4 hours working on that problem this week. So I got it where I can use subprocess to close out of preview. But then when I reopen preview, guess what? All of those images open back up.
Oh, yeah, right.
I've got 1,300 images I'm dealing with. And it's like this should be an easy thing to do. And I spent so much time trying to figure it out. And it was just a disaster. And my internet speed tested out. The highest speed I had this weekend was 0.4 megabits per second.
Ooh, old modem rates.
Well, it was satellite because I was in the middle of nowhere.
Oh, Lord.
Oh, okay.
Like, my cell phone didn't even work where I was. So it's like I'm trying to Stack Overflow this thing. So if anybody has any insight, they can point me in the right direction on how to close the damn windows.
No,
Image got closed, doesn't close the window.
if you have a large data set, wouldn't you be using something like a separate software for labeling, not use notebooks at all?
Well, I was just using Python.
Yeah, but there's like stuff like there's something called Label Box. If you just Google, it's just for labeling. It's just for like, it's a UI for, it'll show up with the images, and then you can put a label in or select it from a drop-down box, and then save the data set into something else.
I could probably do that.
I mean,
but
if you're using
Jupyter
Jupyter for all of that, that's going to be pretty hard.
You wanted to do that with a widget. You want to do the widgets.
Yeah, but even Jupyter, the widgets aren't that good.
Yeah.
So it's
I wasn't even using Jupyter. I was just in pure Python.
Oh, yeah, but yeah, there's definitely software. I know for like labeling.
It's a good idea. Like something you would build for Mechanical Turk, a box. Yeah. Okay.
Yeah, exactly. There's open source. Well, there's paid services that do that, but yeah, if there's also open source tools that basically.
All right, guys. I think we're all going to be part-time employees of NASCAR, thanks to RK. All right. Well,
I wouldn't go that route if I was you guys.
I'll see you next week.